All right, 8.1 is over integrals as net change, and you'll notice that some of these questions are questions we've actually seen previously, but we didn't have the tools that we now have. So looking at being able to use like integrals to help us solve some of these problems instead of techniques we could use previously. So first example says a particle is moving along the x-axis. Its velocity is given by v of t equals 38 minus 4.2 t. Find the following. When is the particle moving right, left, and stopped? So as we look at this, again, how does our particle motion compare to our velocity? When we are talking, when is it moving right, would be when is our velocity function positive? When is it moving left? When is our velocity function negative? And when is it stopped? When is our velocity function equal to 0? And we can kind of start at that last one and use a sign chart to do this. You could set up those inequalities that I had there. So if we just start by finding where t is equal to 0, we can see where it potentially changes signs here anyway. And so solving this one, we would get time equals 9.048 seconds. And that would answer our question of when is it stopped. It's stopped when time equals, so this would be our answer for stopped. Okay, so if we then consider what's going on, again, time's going to start at 0. We are stopped at 9.048. And looking at what our velocity is doing in each of those sections, if we go back to our velocity function and plug something in between 0 and 9.048, like 1, well, 38 minus 4.2 is positive, and so everything in that section would be positive. That would be when our velocity, or when our particle is moving right. Because our velocity function is positive. And plug in something bigger than 9.048, like 10. Well, 38 minus 42 would be negative, and so we can see that our function, our particle, would be moving left when time is greater than 9.048, because our velocity is negative. Displacement. So notice, glancing ahead, parts B and C, again, very related to each other, but the difference between displacement and total distance traveled. Displacement just takes into account where it starts to where it stops, and displacement is going to be the integral on that time. So for the first 10 seconds, our displacement is going to be the integral of our velocity function from 0 to 10. And again, relate that back to the area under the curve is the distance traveled, right? Well, because our integral will take into account the positives and the negatives and just sum it all up for us, we can do the integral from 0 to 10, the whole thing. Oops, I forgot my variable in there, 44.2t. Grab my calculator and type that in, and we get 170 units. And it's positive, which means we're 170 units right of wherever we started on the x-axis. The total distance, however, we have to break it up into the direction traveled. We know that we're moving right, which means a positive distance from 0 to 9.048. So we can set up that first integral from 0 to 9.048 and expect a positive value. And then the next interval that's going to go the rest of the distance from 9.048 to 10 is going to give us a negative value. So again, we can either subtract it, or as I like to do the absolute value symbol here. And again, of our velocity. Okay, so if we go math 9 those, and get an answer, overall answer, we'd have 173.81 units, total distance traveled. Definitely pay attention to the difference between these. So similar. Both talk about distances, but one of them, we're just adding up the areas, positive area, and then subtracting the negative area, and that gives us our total, our displacement. The total distance traveled is doing as we did here and taking negative area and making it positive to get a total area under our curve for total distance traveled. Example 2, now we've got a particle again moving along the x-axis with velocity given by v of t equals 6 sine of t. And this is for 0 is less than t is less than 2 pi. And again, the same questions. When is the particle moving right, left, and stopped? What is the displacement and what is the total distance traveled? So just an example where we do need to talk our trig functions. And again, let's look at the stopped part first. Where is our velocity equal to 0? So then we can kind of utilize a sign chart for each of those to see where is it positive, where's our velocity negative for the right and left part of it. So if I take my velocity and I set this 6 sine of t equal to 0, we'd be looking at where is sine of t equal to 0, or the t equals the inverse sine of 0. So if you consider your unit circle and all the places in one trip around it, because up the top is we're looking at from 0 to 2 pi, which would be one trip around our unit circle. We're looking at where sine has a value of 0. Well, sine has a value of 0 at 3 places in one trip around the unit circle. At 0, at pi, and at 2 pi. And we are including 2 pi, so I put that in my list. So looking at our sign chart to see, okay, if we break up our interval using those times, what's our velocity doing in between those times? So then we just pick something in between those times. So something in between like 0 and pi would be like pi over 2. What is the sine of pi over 2? And that would be 1. That's representing quadrants 1 and 2. Sine is positive in quadrants 1 and 2. Pick something between pi and 2 pi, which would be like, 7 pi over 6. And if I were to do the sine of 7 pi over 6, we'd be talking something negative. It's representing quadrants 3 and 4 from pi to 2 pi, and sine is negative in quadrants 3 and 4. So answering the rest of our questions, it is moving right on the interval from 0 to pi because our velocity is positive, and it is moving left from pi to 2 pi because our velocity is negative, and stopped at 0, pi, and 2 pi. Displacement, again, that is just the interval representing the entire time from 0 to 2 pi. And you'll find, you may or may not find this interesting, but when you go to type this in, your integral from 0 to 2 pi of the velocity to get our displacement. And we hit enter and it seems weird and we get an answer of 0. If you consider your sine curve, this may make more sense. In our sine curve, if I were to draw it with a vertical stretch of 6, from 0 to here's 2 pi. Okay, well, you've got an even amount of area above as you do below. And since displacement will be adding positive areas and subtracting negative areas overall from 0 to pi, we end up with 0 because you have the same amount above as you do below. So the total distance traveled, we do need to break it up between where it's moving right and left. So it's moving right from 0 to pi. And then remember on our moving left part, which would be from pi to 2 pi, we want to make sure that we will either switch it to a positive number in our calculator or type in our absolute value symbols, because this part right here will give us a negative value representing all of this negative area. But typing all that in and hitting enter on that, we get an answer of 24 units. So it must have gone 12 units to the right and then 12 units to the left, which is why we had a displacement of 0. All right, last example today. Particle moving along our x-axis again. And it says we have car moving, just kidding. Car moving with an initial velocity of 5 miles per hour. It accelerates at a rate of a of t equals 2.4 t miles per second for 8 seconds. And so on this one, we have to be cautious because it does kind of switch some labeling on us. But let's also make sure we don't jump over some important information. Initial velocity of 5 miles per hour means that v of 0, initial velocity, equals 5. So on the first question, how fast is the car going when this 8 seconds are up? First of all, how fast? The question is speed. And we have to remember that speed is going to be the absolute value of our velocity function. So we need to find our velocity function. And I can do that with my antiderivative. I know that acceleration is the derivative of velocity. So if I look at then the velocity function, looking at my antiderivative here, we'd have, let's see, that 2.4 t would have come from a t squared. 2 times 1.2 would give me 2.4 and plus c. And this is where our initial conditions are going to come into play, that the velocity equals 5 when time equals 0. So I can set this equal to 5 when time is 0. And we see that c will equal 5. Therefore, our velocity is 1.2 t squared plus 5. Now, speed is the absolute value of that, but if I consider that function, it is all positive. That would be a parabola that has moved up 5. So that entire graph is above our x-axis anyway. I don't have to worry about the absolute value part of it. So now I'm just looking at what is that speed when 8 seconds are up. So what is our velocity? Or actually, what is our speed? Which will be the absolute value of our velocity, which is the absolute value of 1.2 times 8 squared plus 5. Again, the absolute value bars are a little redundant on this since it's a positive value anyway, and that comes out to 81.8 miles per hour. All right, last question. How far did the car travel during those 8 seconds? So how far did the car travel is going to be our total distance. So for total distance, how far did that car travel? We do want to make sure that we are breaking this up by direction of travel. However, again, considering our velocity function to be 1.2 t squared plus 5, that function is always positive. Again, it's a parabola moved up 5. That function will never have negative values. Therefore, because our velocity is always positive, then our car is always traveling forward. Therefore, we don't have to break up our integral into like moving forward, moving back, since it's moving the same direction the entire time. So as we look then at our integral from 0 to 8 of our velocity function, 1.2 t squared plus 5, and I math 9 that, we get 244.8. And at first it seems like great, move on, but then slow down a second. They just said, how far did the car travel during those 8 seconds? And my answer is 244.8. And that seems like a lot to travel in 8 seconds. So then think about what our label is on this. If I go to, again, just looking at our integral here and what we are looking at, this part right here is my velocity, which would be in miles per hour. This is my time, and our time is in seconds. Okay, so our labeling on this would be in miles per hour times seconds. And that's where it gets a little bit ugly on this one. So let's see if we can convert this a little bit here. 244.8 miles per hour times seconds. So if I do a little bit of dimensional analysis here, so that we have the same units, we kind of need to look at the relationship between seconds and hours. And I know that there is in 1 hour, 300 or 3,600 seconds, 60 seconds in a minute, 60 minutes in an hour. Okay, so going back to a little dimensional analysis, that means my seconds can cross off here, my hours can cross off here, and what I have left over will be in miles, but multiplying all the way across the top, all the way across the bottom, we end up with a number that is 0.068 miles. Okay, and that seems like a way more appropriate answer, that we only went 0.068 of a mile in 8 seconds. You could do this also instead of in miles, converting to feet. And if you did that, we could, again, a little dimensional analysis to convert to feet would have been 359.04 feet. Again, seems like a very appropriate answer for only traveling for 8 seconds. Your assignment is on page 390. You are doing 1 and then 3 through 9.